All right. Well, why don't we just get started on the material for today then? So we've been talking some about distributions. Okay. That's what was on the recorded lecture for last week that I started off with. This will help us, especially because when we're dealing with Green's functions, we need to worry about these uh, functionals essentially that are defined based on distributions, and these objects that sort of don't behave as typical functions. And so we define a distribution. So I'll just recap that. So a distribution f acts on a test function, okay? We can call that phi to produce a number, and we can call that f of phi, or sometimes this is written like f with phi there. We know that f of a phi1 plus b phi2 is equal to a f of phi1 plus b f of phi2. Okay, so linearity essentially, where those are scalars and then two different functions. And then we also have continuity. So phi n goes to phi in D, okay, which we define as our space of test functions, right? Then what we have is that f of phi n should go to f of phi, okay? So continuity. And I wrapped up the last lecture by talking about examples. Maybe one that we're very familiar with is the delta distribution. And this just pulls out the value of the test function at 0. You can always shift it around. Maybe another one is the Heaviside distribution, where essentially you just integrate the upper half of the test function. Okay, so that's a sample of examples of distribution. Obviously, for Green's functions, we're going to run into the delta distribution quite a bit. I want to wrap up by just talking about a few more properties, and then I think we'll get back to Green's functions later today. One property of distributions is convergence, which is that we say that fk goes to f in d prime, okay, where d prime is the space of distributions, right? Or we could say it's the dual of D, okay? So we say that fk goes to f in D prime in the sense of distributions. If it's true that fk acting on phi goes to f acting on phi as your series of distributions approaches f for any of the test functions that you have to find, right? So believe it or not, we've already seen an example of this. So essentially the heat kernel phi xt goes to delta of x, and you could index k so that essentially, you could take one over k or something like that. So as t goes to 0 from above. Okay. So the functional basically created by integrating your heat kernel against a test function is a distribution, and the limit of that distribution is the delta distribution. Okay. Derivatives. So can you take derivatives of distributions? You can. Okay. So if I'll call it f tilde is C1 in Rn. Okay, so this is not a distribution. It's the function that comprises the distribution. Then df tilde dxi of phi is going to be equal to the integral over Rn of df tilde dx phi or xi of x, phi of x dx. I can integrate by parts, right? And I can use the fact that text functions have to have compact support so that the boundary terms should vanish. And I'm going to get minus f tilde x d phi dxi dx, integrated with respect to x there. Okay. Rn. And so this is going to be equal to minus f, sorry, make sure I use the right notation here, okay? Your original distribution taken against d phi dxi, okay? So, so what this says in general is that the derivative of your distribution, so me dropping the tilde here, okay, is this f is now our distribution. This is equal to minus f d phi dxi, okay? And it's true for any phi that lives in D, okay? And every distribution is differentiable in the sense of distributions. So for example, we could do this with h of x, right? It's actually not even a continuous function, okay? But once we wrap this in an integral, right, we don't even need this condition of having once continuous derivatives. So if I differentiate my Heaviside function, what does that even mean? Well, that's going to be equal to, in the sense of distributions, minus the Heaviside distribution taken against phi prime. So this is equal to the integral from from 0 up to infinity of phi prime of x dx. Okay, and I can use the fundamental theorem of calculus then to say that this just gives me phi of 0, and so this is equal to delta phi. So this implies that the derivative of the Heaviside distribution is the delta distribution, okay?
Did we drop the minus sign? Oh, no, just kidding. We have negative of a negative.
Yeah, because it's the lower, it's the lower boundary.
Could you say what f tilde is as opposed to f again?
Yeah, so so I introduced it in the last lecture. So this is the generalized function that you're integrating the test function against, right? So it's just trying to be careful with the notation, because this thing that lives in here, this is not the distribution. This whole thing here is the distribution. So I'm just trying to be careful what I call the distribution and what I call this function in here that I'm integrating test functions against. Yeah, it's just to distinguish those. Okay, two more properties. Translation, okay? So it's translation, it's just, shifting things by a variable. So I can translate f's in d prime by y in Rn, okay? And this acts to shift the test function phi that lives in D, okay, by minus y, which is necessarily also in Rn, okay? So if I define the shifted distribution, I'll call it f super y here. This is going to be equal to the integral over Rn over this r tilde, right? That's the function that makes up our distribution when we integrate against it, dx, right? I can change variables to z, which would just be x minus y. So call this thing just z here. And I get f tilde z, because I'm on Rn, there's no boundaries to really shift around because they're all out at infinity. And I have z plus y dy here, okay? So this essentially is the test function shifted by minus y, okay? So for example, we see this a lot, right? And here I'm kind of abusing my notation because I'm calling two things delta. What did I call it? Yeah, now everything's fine. Okay, so this is my delta here, my delta distribution. If I shift it by y, then that's going to just give me back phi of y, okay? All right, so I can translate, if I translate my my distribution here, that's like just taking the value of the test function with y added to it, okay? Last thing is scaling. So how does scaling work? Well, if we take actually a function c in c infinity, so it's a little c in c infinity, c f, let's say, is in d prime, okay? This is defined as follows: cf phi, and all that happens is that scaling function just gets absorbed by the test function, okay? So it's c infinity, so it multiplying two c infinity functions together, we're going to get back another c infinity function, okay? So for example, we can do this, and this may happen if I have a delta distribution scaled by x, then I end up with delta of x phi, okay? Which, because this is going to evaluate this expression at x equals 0, I just get back 0 there, okay? So that's our that's our four properties: convergence. I can take derivatives. I can translate my distributions. I can scale them, and also I have linearity and continuity of my distributions. Okay, and that's going to be useful when we're looking at Green's functions. Okay, questions? All right. Okay, so we're, yeah, go ahead.
since we're scaling by x, which is a non-zero function, and we get back 0, does that mean that like x is a 0 divisor here, or that this isn't a vector space, or like what kind of object are we working with when we introduce the scaling? Is this something new we haven't seen before, or?
I mean, it's just the functional that's defined by integrating, the generalized delta function times x. So I mean, it's a functional, right? But it's a functional that always returns 0. So yeah, I mean, you could say that it's a functional that has whose null space essentially is the entire space of test functions, I guess.
Okay. I guess usually when I think of like functionals, that's a vector space, and we scale it by scalars as opposed to by functions in the, so it
Yeah, right. I mean,
seems different.
yeah, so a scale, yeah, I mean, a scalar would still be C infinity, so it fits under this framework. But yeah, I mean, you're right. I see what you're saying. It's because I mean, the functional itself,
Is the scaling here kind of like weighting an inner product, since we're integrating over these two things, and then now we just threw an x in there?
yeah, I mean, so the way this is defined, right? I mean, it sort of looks like an inner product, so you can sort of think of that. Of course, you're not taking, conjugates or anything like that, but effectively it is, an integration kind of under an L2 inner product, except that you don't involve complex conjugation. Also, this thing here, right, like the generalized function, right, this thing here may not have the typical properties, like it may not even be continuous. It could be piecewise continuous, like in the case of a delta distribution or something like that. Yeah, so it's just because this formulation of the functional, it just involves this integration. You can you often want to know how scaling by an additional function is going to affect things. So that's why we would expand this definition to include scaling by functions, right? But of course, you see, like back here, right? If you scale by, if you just scale by a scalar, then you can just pull the scalar out. I mean, like the typical thing you would expect with a linear functional. Okay.